Hello folks, welcome to CS-412 Software Security. This is a speedrun of OX08 testing. We've now completed all the generic topics on software security along with talking about different kind of mitigations. Mitigations prohibit the exploitation of any remaining vulnerability in the code, making it harder for an attacker to gain code execution for bugs that are in code deployed to the customer. We'll now talk about different kinds of software testing, where bugs are being found and removed by the developer before they can do any harm. So this is a technique that enables the developer, as in you, to get rid of any kind of security vulnerability before code is actually being shipped to a user or a customer. The learning goals for today are to understand the benefits and limitations of testing. How far can we get? How complete can we develop these tools? How many bugs can we find, and what are the different kind of trade-offs? So you'll be able to list different forms of testing and their trade-offs, from static to dynamic approaches, from fast approaches to slow approaches, to complete approaches to incomplete approaches, along with the trade-offs on these different dimensions. You'll be able to get to explain key testing terms like coverage, state explosion, or metrics, and also differentiate of what can be tested and what not. Why would you need testing? Well, testing is the process of analyzing a program to find errors. As developers are human, there will always be bugs introduced because of a missing specification, a misunderstanding of the constraints, or some other aspects that were unclear and unspecified. An error essentially is a deviation between the observed behavior and the specified behavior, and therefore a violation of the underlying specification. Assuming that we have a form of specification of what the code should do, we can test for a given violation of it. If the program does something it shouldn't be doing, then we can actually report that. The specification can contain functional requirements such as different kind of features, as in different kind of command switches that should exercise certain functionality. It can be operational requirements such as performance or usability. It needs to complete a sorting of an array in a certain amount of time. There could be a performance operational requirement, or it needs to handle up to 10,000 customers or transactions per second or whatnot. Or usability, right? It needs to be easy to use. It needs to have a text-to-speech feature or whatnot. But security features or security requirements are somewhat unspecified. As in, security is the absence of any kind of policy or specification violations that would allow the attacker to achieve their goals. And this is very vague and very hard to actually specify, and also often not actually covered. So security requirements are extremely hard to define. And this also leads us to a limitation of testing, as testing can only show the presence of bugs, but never their absence. Especially on larger code, it may be incredibly hard to discover it or to prove that there's no bugs in the code. And testing will simply check for the presence of bugs, but thereby potentially give a witness of the bug or an indication of where the bug actually is. Because a successful test will find a deviation and actually serve as a witness of an issue. So testing is a form of a program analysis, as it looks at the program, looks at the specification, and then searches for violations or deviations. Code is analyzed, the testing environment observes the behavior of the code. This could be the execution of the code, the analysis, the abstraction of the code, the semantic exploration or whatnot, and then detect and signal violations to the developer, so that the developer can then take these reports and go and fix their code. The requirements for specification will help the developer to actually fix and find these issues. Testing checks whether the implementations agrees with the specification, as in, like, it tries to match specification to implementation. And this requires us to actually have a specification, because without specification there is nothing to test, right? If we don't have a specification of what the intended functionality is, we cannot decide if something we observe is unintended functionality. So the testing or the test serves as a strict consistency check between the specification and the implementation. And usually the specification should come first, specifying of what is needed and then actually implemented. And then we can check for a match if the two actually are correct. Testing enables this quality metric in software checking and allows us to do this analysis. Now, if both the specification and implementation are incomplete or wrong, there is an opportunity for false positives and false negatives, right? And in our world, in the real world, both the specification and the implementation will be incomplete and potentially be buggy, and this will lead to interesting issues that you can potentially solve with with testing across multiple specifications or across multiple targets. But this is generally a hard problem to look at, but usually not the hardest problem to look at, because often a mechanized specification is not available. Therefore, we don't have any machine checkable specification that we can use to compare against. A lot of the issues will actually, or a lot of the functionality will be specified in prose, for example, through documentation or whatnot. And this is not necessarily machine checkable. So what we need is an oracle, right? For any form of check, we need an oracle that tells us that a fault has actually happened, a violation has occurred, that allows us to detect that there's an issue. The goal of testing, as I already said, is to detect violations of a specification given an implementation. The specification and implementation are concrete instantiations here, and the specification defines these illegal operations given the policy. Now, we need to be able to detect these program faults, and the oracle will tell us, hey, a fault has just occurred, you need to go fix this. And the test cases can detect bugs through a set of different issues. And an oracle can be, for example, an assertion, like that signals you that, hey, I've encoded that this value should never be OX23, and if I observe at runtime that the variable is OX23, I will actually report that there's an illegal value and give the programmer a signal. It could be a segmentation fault if you're writing programs in unsafe languages due to an out of bounds or invalid pointer, division by zero for a floating point exception, different kind of uncalled exceptions in if you're writing Python code or even C++ code, and a mitigation could trigger termination. For example, a mitigation like control flow integrity could serve as an oracle to highlight that a pointer has been corrupted because it's executing these additional checks. Well, how can you now increase the chances of detecting a bug because the oracles may be incomplete? You could augment your code with checks that validate your specification and even have a mechanizable or machine checkable specification in the first place. And later on in the sanitizer lecture, we'll cover different kind of fault detection environments and how you can enforce certain kind of policies to check for violations of specifications. For example, enforcing memory safety or an abstraction of memory safety to test for memory safety violations of the code that will signal you specification violations or undefined behavior at a more precise level than simple segmentation faults. We'll cover three forms of testing in this block of classes. Today we're going to focus on introducing manual testing, some simple static analysis, and a glimpse at dynamic analysis. Manual testing is a human testing the code, a human developing individual test cases, and this can be on the basis of unit tests or full end-to-end program tests. Static analysis will analyze the program without executing it, as in it abstracts across all possible executions. Right? So this is an abstract interpretation of the code, where the code is being transported into an abstract domain that allows us to verify or check for certain properties, thereby generalizing across the whole source code, and then analyzing the constraints without actually executing it. The large amount of these constraints often results in some form of state explosion, either limiting scalability or introducing false positives. Dynamic analysis, on the other hand, analyzes the program during a concrete execution, so there's actual code being executed. Dynamic analysis focuses on a concrete run, but this gives it a more limited view, but very detailed information for this given execution, right? So while you cannot speak for the whole program and the full program state space, you can talk about one single aspect of the program, right? So static analysis covers the full program state space through an abstraction. The dynamic analysis will cover one single execution, but then go into detail there. If we classify testing using a couple of examples, manual testing will be printf, unit tests, or integration tests, for example. Static analysis could be compiler warnings. That's the static analysis you're most used to. Fast checkers such as linters or per unit checks, or even heavyweight static analysis as the clang checker framework. On the dynamic analysis, we are using more heavyweight instrumentation and analysis. So this could be white box testing, where we are aware of the functionality specification, so we are looking into the specification. Gray box testing, where we're partially aware of the specification, or black box, where we're unaware of the specification. Now here in this class, we're focusing on security testing, or testing to find security bugs, as in bugs that are reachable through attacker-controlled inputs. And issues like unit tests or individual smaller abstractions or smaller levels are not that interesting for us. If the bug cannot be reached through attacker-controlled input, it is a bug and not a vulnerability, and of less importance for us. If you look at manual testing in more detail, the goal here is to create test cases by looking at the specification, which is potentially written in prose, and then come up with individual test cases. So you would iterate the following steps until you run out of resources. And we'll actually have a similar approach in other testing mechanisms, like symbolic execution or fuzzing, which we'll hear in the next class. You keep iterating until you run out of resources and try to cover as much as possible of the program state space. In manual testing, you read the high-level documentation, understand the functionality, get familiar with the code structure, then draft test cases that cover the requirements from your documentation and the component that you're most interested in, review and discuss the test cases, execute them, report bugs. After bugs are fixed, execute test cases again. So the benefit here is that after going through one cycle, you have a set of additional test cases that allow you to test certain properties. So for example, whenever you change aspects in the code as software evolves, you can rerun these existing tests. And by repeating this process more and more, you will accumulate a large set of test cases that will then allow you to go find bugs or regression bugs as they are being reintroduced. Right? So over time, manual testing results in this very large set of test cases that cover all the different aspects of your functionality. And just as an example, running test cases for large software can sometimes take hours to simply evaluate if all of the tests are still true, right, after changing code. Manual testing is extremely widespread due to its simplicity. It already fits into the development cycle. You can just create a new little program, create the mock environment and set it up. It's very straightforward to set up, very straightforward to execute. Simply add a test target to your make file or to your build environment, and it gives very good feedback if test cases are carefully designed. Manual testing has some limitations though, right? It requires manual effort to create each test, to create each input, and there may be like blind spots for a developer who may be missing certain aspects of the documentation or of the API or the edge cases that they are simply blind to, right? And the tests must also keep up with the development. As the requirements and the specification evolves or changes, the test cases need to be adopted as well, which may pose certain difficulties, right? And ideally, a manual testing will cover large parts of the source code, as in it will cover a large chunk of the underlying target application, or of the underlying code. And coverage means which parts of the code are actually executed and covered. If you're moving on to static analysis reasons about the code instead of executing it. So it's an abstraction of the code to a abstract domain, allowing later interpretation. The line between static and dynamic analysis is a bit blurry, because even a static analysis will abstract the code and then execute some additional code on behalf of the application. But in more general terms, a static analysis looks only at the code without keeping track of concrete values during execution. The advantage of static analysis is that you'll get full coverage, as in all the code in the program is being analyzed and being reasoned about. So there's no need for complete test cases. There's no need for a lot of additional manual effort when you create new functionality. It is also complete, right? As I mentioned before, test cases may miss edge cases. It also doesn't need a runtime environment, as it runs in an abstract environment that allows you to reason about these different aspects. The disadvantage is that the computation depends on data, resulting in undecidability. Like in the real world, there are things that are just not decidable, and a static analysis cannot reason about concrete values. As in, if something depends on input, the static analysis will not have this input available, because it simply can only reason about the source code that it has. It doesn't know in which context it will be executed later on. Similarly, the over-approximation will result in imprecision, right? So there's imprecision, aliasing, and whatnot that will limit the static analysis and result in over-approximation that will introduce false positives. And this is one of the major issues that static analysis actually have. There's a great paper, a few billion lines of code later, using static analysis to find bugs in the real world. That is very highly recommended. You should go look at later. Now, what do I mean with static analysis and limitations of static analysis? One of the big issues, as I mentioned, is undecidability. So if you look at this program here, we can analyze it, we can look at it, and we may ask ourselves, can this assertion ever trigger? So can X ever be 24? We'll look at the code, we'll stare at it, there's a user input, and we can actually see if Y is 0, then the program is faulty, right? Because if Y is 0, then not Y is true, and therefore X will be incremented to 24 from its initial value 23, therefore the assertion will trigger and the program will crash. Okay, so far so good. So we looked at this program for long enough, we stared at it, we reasoned about the code, and we discovered that yes, we can trigger the assertion by supplying a specific value that makes Y 0. Okay, so you also see that there's only 1 over 2 to the power of 32 values that will actually trigger this bug. So it's highly unlikely to randomly find this input that will trigger the bug. Now here we can reason about it. What about here, right? Will this assertion ever trigger? If program P terminates on input I, then we increment X. Well, at runtime it may or it may not. But we've just made it dependent on solving the halting problem, right? So therefore, this becomes undecidable. And static analysis is limited by the complexity of the constraints it can handle, and it can certainly not solve the halting problem in reasonable time. So the majority of static analysis tools therefore over-approximate, simplify the analysis, and then rank the remaining results. So let's recap. Static analysis tools reinterpret and analyze the code. They may run at different levels of abstraction. So they may be running at the preprocessor, level in the compiler at the abstract syntax tree, parsing tokens or doing some lexing, or even as a more involved analysis on the level of a control flow graph as a high-level code representation. Static analysis frameworks are often extensible and can leverage different kind of plugins to implement certain checks. And we'll talk about some more of them later on that you can try out. But first, I would like to highlight the 8 laws of static analysis. So these are not exactly laws, but more like guidelines that you should look at. And they are: you can't check code you don't see. You can't check code you can't parse. Not everything is implemented in C. This is not a bug. Not all bugs matter. False positives matter. False negatives matter. And that annotations are extremely costly. Let's go through them one by one and add a little bit of context to that. Law number 1, you must see all code. So if you're developing a new static analysis, it turns out that you cannot check code that you don't see. And developing static analysis, while a great academic example, is actually a fairly hard task to get it used inside a company by developers. Build systems are extremely and incredibly complex. It takes a lot of time to configure a build system, and just simply changing the compiler or the build environment is often not possible for reasonably complex program. So the static analysis must tie into the existing build system, as in, for example, a drop-in replacement for the compiler command or whatnot, that then simply collects all the information. So law number 1, you must see all code, or your static analysis must see all code. Law number 2, parsing is hard. As in, you can't check code that you can't parse. So building on top of existing compilers is the most reasonable approach, because you can simply leverage the parsing infrastructure of existing compilers. Quickly hacking up a parser on your own may work on a couple of toy examples, but it will not scale to very large and very complex code bases such as, let's say, Chrome or like the Linux kernel. Different compilers, different versions make parsing all really, really hard. And the static analysis often focuses on this single compiler setting, right? So you must scale to all these different compilers and environments to be able to parse large sets of complex code in a realistic environment. Which kind of leads me to the next law, law number 3. Not all code is C and C++. There may be preprocessor micros in there, there may be inline assembly in there, and so on. And the static analysis needs to be able to abstract across all the code, and not just your C and C++ code. Right? Large sets and large parts of the systems are implemented in other languages, such as auto-generators for bindings, protobufs, whatnot. There could be binary code or libraries, or even like some code maybe in old and obscure dialects of C and C++. That when was the last time you wrote Carnegie-Ritchie C, right? So there could still be code out there that needs to be compiled. Law number 4, a bug is a bug. Well, this may be up for interpretation. You may not know if this is actually a bug or an unintended feature. This could not be a bug. And as it turns out, understanding large code bases is hard because of their complexity and their dependencies between each other. It could be that the author left the project a long time ago and whatnot, right? So the static analysis must be able to give sufficient context to reproduce and understand the bug. So if a static analysis believes that there's a bug in a certain location, it needs to give the developer a sufficient amount of context and details to convince the developer that this is actually a bug. Otherwise, the developer will simply ignore the report. In the same path, a minimal test case would be ideal. Like if you have a proof of concept that this is a bug, then it is much more likely to be fixed than a vague statement. Hey, there, at this location somewhere in the code, if these things happen, then maybe there's a potential issue. This may be sufficient to add an assertion, but it would usually not be sufficient to cause large set of code changes. Law number 5, all the bugs matter. While you may think that all the bugs matter and should be fixed, It is an unfortunate truth that there's simply too many bugs to be fixed. And not all the bugs are equally important, right? So if you consider a static analysis that finds 20,000 bugs, which of those would you like to fix first? The resources are extremely finite, and you need to rank bugs somehow to severity. So the ranking of the bugs and issues is incredibly crucial for you to for a static analysis to be efficient, right? Even though all the bugs should be fixed, in reality only a few bugs can be fixed due to limited resources, and this gives you perspective on when and what to fix. Law number 6, false positives. False positives matter, right? A static analysis must have very low false positives. Each false positive must be analyzed, or each report must be analyzed, right? And false positives thereby incur additional cost, as developer time is being spent to look at code that is not buggy. Unfortunately, these false positives exhaust developers, but unfortunately they are also part of any static analysis due to different levels of imprecision or over approximation. If there's too many false positives, the developers will give up. And here again, a ranking matters. The static analysis need to be able to decide, hey, this is most likely a bug, and this is something that we will have to look at. In the same vein, false negatives matter, right? Any false negative is a bug that is missed, that will not be covered, that will not be found. So the static analysis must be carefully tuned between too many false positives and too many false negatives, and cover this nice middle ground where it effectively finds severe vulnerabilities and can then push and search for different issues, exploring this trade-off at being a useful tool, helping the developer find and fix as many vulnerabilities as quickly as possible. Law number 8, the last law, the annotations are costly. Annotations are costly, right? If you are running a static analysis on a large code base, it is quite an effort to introduce new annotations to the code base. Similarly, annotations need to be maintained. The developers need to continuously spend effort on maintaining and keeping the annotations up to date. So a static analysis must support some form of incremental annotation to allow like gradual development of annotations across the code base. And this is an interesting requirement here, that for realistic code bases, it's just not a one-shot effort to quickly turn on a static analysis and run the analysis after adding a couple of annotations. This often takes many years or a lot of time to actually deploy, right? So it may take several people quite a long time to deploy this on this larger system. So what does a static analysis actually look like? So let's go through a couple of examples, right? Here we've got this code, and we may be interested in what the possible definitions of each use are, right? So if you look at the code here, we have 3 variables, z, x, and y, that have a couple of assignments, a couple of conditionals, and we may want to figure out what all the possible values for y, z, and x are. So we can go through the code, we can analyze it, we can look left, we can look right, we can keep track of all the different things, and then we can develop a set of targets, right? For z, we can look at the assignments. Z is being assigned once to value 4. X is being assigned once to value 2 and value 3. And this gives us the set of y, because it is the union, due to the last condition, of the 2 sets, right? So we've run a set analysis that gives us an interesting way to determine possible definitions of values, right? Similarly, this could be used for call targets, and we've covered CFI in a previous lecture. Here we could figure out what the possible reaching definitions are for this dereference, for this call to the function pointer p. Right, we've got p and q. These are two function pointers that have different kind of values, and both of them are assigned multiple times. And if you track the flow of the program, we figure out that Q is assigned F2 and another time F3. So Q can be F2 or F3, and P, if you go backwards, can be either F5 or Q. So P can be F2, F3, or F5, right? So the reaching definition at the point P are either F2, F3, or F5. And this is much more precise than the initial analysis that would simply collect the superset of all the possible assignments. So if you would only look at the assignments, P could be F1, P could be F4, that are all not part of the final set at the end, right? So this gives us a much more precise information, limiting the possible values. And now you see here, based on the static analysis for P, we have 3 possible function targets that can be reached. At runtime, only one will be possible, dependent on the values of P1 and P2, right, of this predicate that will be evaluated. So at runtime, we will only have one possible value, while statically we can determine using our precise analysis that we just ad hoc develop that it will be one of the 3 values, F2, F3, or F5. Right? So this is the difference between static analysis and dynamic execution of a single run. Another example, what are the possible ranges of a variable? What is I for value 1, like between value 1 and value 2. Right? And here we can actually look at the execution. It's an input that is being loaded. And here we want to demonstrate what the possible values for I are. As a first step, we actually run and turn this into static single assignment. So we iterate through all the possible assignments and make them explicit, thereby allowing us to track the individual like ranges for this range abstraction. If you look at I4, like I4, the assignment here is either I2 or I3, depending on the if condition. Like if I is larger than 10, it is either between 0 and 10, because that's the upper max that's being cut. And either depending on the abstraction for I4, we can keep track that is between 0 and 10, or that it is between it is 0 or 10, right? If you only have the upper bounds. If you continue like this, I5 is the addition, x is equal to 10. So at I5, we know that it is between 10 and 20. At I6, we know that there's a subtraction, so it's between 6 and 20. And then at I7, if you continue this, it's again between 6 and 20. And this gives us the full range of the possible targets, right? So it's the upper range of the union between the two. So we have a union of I5 and I6. Therefore, the range is between 6 and 20. And we know that this is the final range. So we've now developed an analysis for this possible range of this value that could then be used in a constraint analysis later on to figure out how possible test cases should be created or whatnot. We have now intuitively and in a very ad hoc and very informal manner developed 3 different static analyses. We've only talked about what they should do, but they implement 3 interesting examples. Example 1 would be a reaching definition for the target. Example 2 would be a data flow analysis for the function pointers. And example 3 would be a range analysis for static single assignment here. Now you don't need to go too much into the details of these different examples, but simply be aware that there's different kind of static analysis. All of them interpret the code, abstract the code, and then develop some information that can be used later on to test certain behavior. For example, for the range check that we've seen could be used to analyze if there's possible violations of constraints later on in an assertion. The function pointer analysis the data flow analysis that we looked at could be used for control flow integrity, right, or some other abstraction there. Now, the requirements for the static analysis are the abstract domain, like what is actually computed, what is needed by our static analysis, and where do we need this information. And we then need a transfer function to abstract the values into this abstract domain, allowing us to update the values accordingly. So in the range analysis, we didn't calculate or didn't compute with concrete values, but ranges. So concrete values were replaced by the ranges that we kept for the different values. So we must consider the instruction semantics of the transfer function, as in merging the two parts of I5 and I6 into I7. Combining the two ranges is a different operation than simply adding a certain number, right? As this has different semantics, so we must consider this instruction semantics for the transfer functions alongside. Now, if you look at static analysis, there are certain challenges here, right? When shall we terminate a loop pass? How many iterations of a loop should we consider? Is the loop bound? How do we infer different kind of variables and whatnot? We are interested potentially in the aggregation of these abstract values along the pass. We have to decide when we stabilize. Is this a fixed point iteration? Can we just grow monotonically and assume that the domain is finite, right? There's a lot of different aspects that we have to consider depending on the static analysis that we are implementing, right? So there's a lot of interesting things that you need to consider if you want to develop your own static analysis based on a certain property you want to test. Now there's certain levels of static analysis here. If you focus on clang, for example, there's warnings. That's the most simple level that you can do. It's like a first line of defense. You simply turn on a couple of warnings during compilation. These are fast, have a low false positive rate, and often build on AST, preprocessor, and CFG. You should check those for all builds, both debug and production, and simply go through them whenever you can. Clang tidy is already a bit slower and has a slightly higher false positive rate. So it checks for coding conventions, different kind of third-party API check, matches ASTs, inspects preprocessor information and whatnot. You check for debug build and, for example, during daily regression. And then last but not least, you can run the clang static analyzer, which is slow and of fairly high complexity. And some techniques here have then higher false positive rate, but they may also give you a certain level of issues that they report, right? So this gives you much more precision on the information there. For example, running during daily regression with the analysis of the report afterwards is a good strategy. And I actually invite you to look into clang tidy and the clang static analyzer for more information on it and how you can turn this on for your projects. In its simplest form, the compile time warnings simply give you information about the code and potential issues of the code. With compiler warnings, the goal is to highlight issues in the code and to give feedback to the developer. It must be fast, low overhead, must be simple, and very, very low false positive rate to limit warning fatigue. So for example, you can run clang, W all, W extra, W pedantic to have basic set of warnings, extra warnings that are a little more detailed, and pedantic, which warns about anything that goes beyond the strict C and C++ dialect that you're coding for. You could also turn on W everything, which just gives you every single warning that exists. But this often creates a lot of noise. Now, as you're working with warnings, you may want to turn warnings into errors, or you may consider turning warnings into errors. And this comes with a caveat that it doesn't really make sense to turn all the warnings into errors, because compilers change, right? If you're doing this for your own little toy project, this may be fine, But for large and complex projects that are being used as part of a build chain somewhere, this may result into weird issues somewhere along the way. Optimizations can become very complex, and the compiler may result in suddenly terminating the compilation of a project that is deep in your compile path somewhere due to an error that is not actually an error, but simply the compiler becoming a bit more verbose on different issues. So yeah, consider this in your project, but not necessarily in large projects. Now, lightweight linters, clang tidy. It's a C++ based linter tool where you can implement certain checks as plugins, and they're actually fairly simple to implement and extend. And then checks can cover different platform, coding conventions, libraries, APIs, whatnot. Checks are limited to the current scope or compilation unit, and think of this as glorified warnings sprinkled with some constraint solving to highlight potential issues in the code. And you can check out clang tidy here, and you should use it in your targets. If you want to be a bit more heavyweight, you will use clang static analysis, and the clang static analyzer plugs into the build system, and then during the build we'll run certain analysis plugins on top of it that cover different kind of areas, such as at its core, null function pointers, logic errors, division by zero, null dereference, just a lot of undefined behavior. It can be programming language specific, such as double freeze, use after free, whatnot. Dead code, different kind of checks for uninitialized objects, some security issues using insecure functions, or certain APIs. Right, so these are very heavyweight analysis across the whole subsystem that's being run, and you can run it for your target system by plugging into the build system there. You should check this out as well. Now, static analysis comes with limitations. There's this inherent trade-off between soundness and completeness. Soundness would mean you find all bugs of type X, and finding more bugs is good, but also soundness is costly because checks are weak, or the complexity could explode due to the program state space that needs to be explored. There's also diminishing returns. The initial analysis may find a lot of bugs, and then you need to exponentially spend more and more time on the few remaining bugs as we go further and deeper into the code. Right, so there's an inherent issue with completeness of static analysis, but also with soundness, and you need to tune this trade-off accordingly. On the other hand, if you look at dynamic analysis, we are actually evaluating a concrete execution of the program. And as mentioned before, we've got the three angles: white box testing, which would be symbolic execution; gray box testing, feedback-oriented fuzzing; and black box testing, where we will look at black box fuzzing. We'll have a quick peek at symbolic execution today, and then more about other dynamic analysis next week. Symbolic execution is, think of it as an abstract interpretation of the code. Instead of having concrete values for your variables, the values become symbolic, just as in math, right? A mathematical statement or mathematical formulas. And values are symbolic and no longer concrete. And it's completely agnostic to concrete values, and we simply aggregate individual formulas. Constraints concretize formulas as we are accumulating more constraints and we're executing additional statements. We are expanding a program into a set of constraints, collecting these formulas, combining them, and thereby translating an execution of the program into a set of into a logical formula that we can then evaluate. Right, so symbolic execution engine will have the statements of the program with a set of statements to evaluate, symbolic store, which contains all the information about the variables, the path constraints along the current path that is being evaluated, and then calls into an SMT solver to figure out if something can be satisfied or not. Symbolic execution defines a set of conditions at code location. Then the symbolic execution determines a triggering input, and this is one of the key benefits of symbolic execution. It actually gives you a concrete input that will violate the target program if given sufficient time, right? So it is a testing technique that finds bugs in application and generates a proof of concept input through SAT or SMT solving. Now, in symbolic execution, bug conditions must be clearly defined. And one of the big issues that symbolic execution has is state explosion. Symbolic execution needs to evaluate each possible pass through the program, which very quickly explodes due to the massive amount of complexity in the current program. Either the length of the constraints or the amount of states doubles at each loop iteration or conditional. Right? Whenever you execute a loop, each loop iteration just doubles the length of the constraints that you're collecting through the program, or it doubles the amount of the paths that you'll have to evaluate, right? So you have this inherent trade-off between making the formula more complex or increasing the number of paths that you have to evaluate. So searching valid paths is crucial. Path optimization and state pruning are other key research areas. And this complexity inherently limits the scalability of symbolic execution. So let's go through a concrete example. We've got this function here that takes 3 parameters, a, b, and c. And inside the functions, we've got a couple of conditions. If b is smaller than 5, and if not, a and c. And then we set 3 local variables, x, y, and z. And then we check if the assertion x plus y plus z is not equal to 3. If it is equal to 3, we will trigger a bug and terminate. Now the question is, can the assertion ever be triggered? Now a symbolic execution engine will look at this as follows. It will store the state of the variables for x, y, and z using static single assignment, and then go through the program on a condition basis. So it will iterate through all the possible paths through this function. The first check is if a, and we check if a0 is true. If it is true, then we set x to -2. We update the state store for this path and execute the second condition. If b is smaller than 5. If true, we will open the if statement and execute the code in there, and then check if not a and c, and then we will assign y, and always we will assign z. Right? So along this path, we will assign y equals 1 and z. So we have collected a condition of a0 and b0 smaller than 5, and not a0 and c0. This is unset, right? So this is an infeasible pass because both a and not a are true. Therefore, the symbolic execution engine will drop this pass. Next step, we will evaluate if this condition is not true. Our collected pass is if a0 and b0 smaller than 5 and not not a0 and c0. We can evaluate this. Evaluate it with the state and the program variables, and we will see that in the assertion that 0 is not equal to 3, which is unsat, all good. We'll go to the next pass. We'll collect it, a0 and b0 larger 5. Again, this is unsat because -2 is not equal to 3, so we are not crashing. Now we're assuming that a0 is false. Again, we copy the whole tree. b0 is smaller than 5. We again check for not a and c0. And here, the SAT solver will actually give us a satisfying assignment and say, hey, we've got the satisfying assignment, and here's the concrete example. A needs to be 0, B needs to be 4, C needs to be 1, and then we've got a violation. The 0 plus 1 plus 2 equals 3, therefore assertion triggers and the execution terminates. Right, so we've got a concrete example that will trigger a violation, and symbolic execution has found a bug. We'll continue for the other pass until we've exhausted all the possible paths. So we found one bug, one bug in one pass, 4 paths that are not buggy or correct, and 1 infeasible pass out of the 6 paths that we have evaluated. So far so good. We can now highlight the buggy pass through which will tell you how the assertion will actually be triggered at runtime using the information that the SAT solver gave us. So far so good. Now we've learned a bit about symbolic execution, and running tests once is great, but we'll actually have to run those continuously, right? So we have to integrate testing into some form of continuous integration so they can be run for each commit. And it's somewhat of an orthogonal topic, but just as a hint for you to run this as part of your build process, right? So you should integrate this into a continuous integration system such as Jenkins or whatnot, which will run your tests at fixed intervals. For example, daily or even for each commit as much as you want. Continuous integration is only as good as your test cases and your setup, but set it up together and make sure that it actually is being deployed. It also ensures that changes comply with your specification, checks for regression tests, and whatnot. Now, we've talked about some different aspects here, and you may have heard about other testing tools or ways to find bugs. And I just wanted to give you a bit of a comparison between analysis, so that you can kind of rank this along different dimensions. Formal verification is the strongest tool. It gives you completeness, and it will give you complete certainty about the security of a code. It will find all bugs, but it is extremely expensive, both in labor and in computation. It will scale to hundreds of lines of code, but it will give you extremely high certainty about the quality of the code or the bug freeness of the code. Bounded model checking is a somewhat relaxed form of formal verification, which scales much further to, let's say, thousands of lines of code, and will find most bugs. And it kind of scales formal verification by constraining the loop bounds that are being analyzed and adding these checks. Symbolic execution may scale to 10,000 lines of code and find all bugs if it runs to completion. But running to completion is kind of hard. Concolic execution then scales symbolic execution even further, 50,000 lines of code, finds bugs close to the provided concrete execution, thereby using some form of context to abstract complex execution, but cannot reason about the whole program, about all paths. So it already gives up completeness. Fuzzing fully gives up completeness, but scales to millions of lines of code and finds many bugs in complex environment, and is one of the most effective used testing techniques today, and will be the topic of the next lectures. Last but not least, we've also covered warnings and simple analyzers, which scale to everything and find lots of interesting locations at potentially false positives. So, as a summary, software testing finds bugs before an attacker can exploit them. Testing requires a specific policy or a specification. You should always check if the code follows the policy specification, integrate testing into your development practices, and certainly be aware of the laws of static analysis. Check all code, find important bugs, be aware of trade-offs between false positives and negatives. When you come up with new systems, make sure that it actually runs, and tune those towards these different trade-offs. Remember, static analysis is over an abstraction domain and must terminate due to the finite amount of resources available. Transfer functions to transition between the states, and then we've discussed different sets of analysis that all have different kind of trade-offs that we can look at. This is all for today. Thank you for your attention, and I'll see you next time.